Hi, everybody. I hope that everybody is doing well. Before we get into the lecture today, I just wanted to go over what we're wrapping up from week 13 and what we're going to be getting into this week for week 14. So last week we went over the second half of chapter 9 in the Bolstad text. There was the third discussion, which is going to be due April 21st by 11:59 p.m. And so remember, you do have an entry that you need to submit, and then you need to respond to one other student. You'll need to complete Lab 9, which is also due April 21st by 11:59 p.m. And then, kind of most importantly, there is a reading quiz on chapters 8 and 9 in the Bolstad text. I extended the time for the quiz. It's going to be open until 11:59 on April 21st. So if you have not taken that quiz, please do. There's not really like a flexibility for a late submission for that kind of assignment. So if you aren't going to be able to get that done by April 21st, then please let me know. So at least we can discuss your options from there. Okay, so for this week's module, for week 14, I'm gonna do this a little bit differently. There's a lot of information to cover. Normally this would be spread out over 2 weeks, but we just don't have the time for that with everything that I want to squeeze in for the rest of the semester. So normally I would be having you guys read both chapters 10 and 11 for this section. I know that's a lot of reading, so I've broken the chapters down into what I think you should be covering. If you have time to read both of the chapters, please do. There's a lot of information in there that can be really helpful, not only for the lab activities, but for understanding raster and terrain analysis on a deeper level. Okay, so there is also going to be another discussion that you'll need to participate in and complete. That's discussion 4, which is going to be due April 28th by 11:59 p.m. So you will have a submission and also be required to respond to one other student. And so there are, you will be required to create a flowchart in Word or PowerPoint. I included a video on the discussion page on how to do that. If you're having any issues with either of those programs, please let me know. There's also another lab activity, Lab 10, which will also be due April 28th by 11:59 p.m. And just a reminder, I'm available to help between the office hours and regular class hours on Tuesdays and Thursdays between 5:30 and 8:30 p.m. If you need help on a lab, have questions about the class, please contact me beforehand so we could schedule a time for us to set up a Zoom meeting or figure out a way to troubleshoot if that is not available to you. Also, this week's module is going to be split up just a little bit differently than the last few weeks. So I'm going to have this lecture video available on April 21st, Tuesday, and then I'm going to have a second lecture that's going to be available on Thursday. Just because, like I said before, there's a lot of information to cover, and I want to help split up your week a little bit by doing that, so you could focus on getting the discussion going and the first part of the lab, and then the second half of the lecture will cover the second part of the lab and the rest of the readings. Okay, also a lot of this lecture should be familiar to you. You should remember it from our lesson on raster models. And so if you need a little refresher, you could go ahead and check out that PDF lecture that is available on Canvas, but you could also just focus on the new information and this lecture video. So there's a fundamental difference between raster and vector data models. Their construction determines the dissimilarity between the two. As we discussed in the data model lessons, rasters are a grid of square pixels. The vector data model does not have pixels. Instead, line segments connect nodes and vertices. The computer keeps track of line segments through a series of mathematical equations that keep track of length and curvature. In a vector-based image, you can scale infinitely without pixelation occurring. There can be no gaps in raster data, so even if a cell does not have data, it must be assigned a placeholder values such as no data. Raster data is most often used to store attributes that represent a continuous phenomenon, such as snowfall, temperature, slope, or elevation. The elevation values in a digital elevation model are an excellent example of a continuous phenomenon, since there is no point on the surface where elevation does not exist. The raster data model works well for storing types of data that have a lot of different values for one attribute. Each cell records its value of that attribute. In this image, each cell stores a number, and that number represents an elevation value in meters. A raster dataset can record the elevation values across the region, constrained only by the size and number of the cells. On the screen, a computer translates those values into colors, such as shades of gray. To the computer, a raster file looks more like this image here. In geospatial science, we usually refer to a pixel as a cell. When looking at raster data, each cell represents a distance and an area on the ground. The length of the ground that each side of the cell represents is called the cell size, also commonly referred to as resolution. There are several limits that you must be aware of when dealing with raster data. As I mentioned before, each cell can only hold a single attribute value. The value represents the entire area covered by a cell, which is a simplification of reality. For example, a digital elevation model with a cell size of 30 meters assumes that the elevation across the entire 900 square meters are equal. In reality, the elevation may rise or dip lower in places at that location. As the cell size increases, information gets lost as it becomes generalized or averaged. Another problem can arise when the cell size is too small. A decrease in cell size for any given area means an increase in the number of cells overall. The increase in the number of cell places a much higher demand for computer processing requirements and data storage. Okay, so terrain or surface analysis is a type of analysis that involves the study of variables which pertain to the surface of the Earth. Most terrain analysis are performed with using raster data, which is a subcategory of raster analysis. All of the terrain analyses that we will be covering in this class will be using a digital elevation model, or DEM, as a base layer, and we will be using various functions in the ARC toolbox to process DEMs for these analyses. So what we're going to go over in this lecture is elevation, slope, aspect, and these are going to be mixed up a little bit, but this is an example of a view shed, and this is an example of a hill shade. And you guys, like, not only are we going to be going over this in this lecture, but you'll be creating all of these except for the elevation model, which will be provided to you for Lab 10. Okay, so a digital elevation model, or DEM, provides a representation of surface topography or elevation in a two-dimensional space. DEMs are a 3D representation of a terrain surface, such as the Earth. Typically, DEM data can be represented as a raster which is most easily expressed as being a 2D array with each individual cell having an elevation associated with it. With a DEM, you can analyze certain derived quantities using pre-built software. Digital elevation models are created by a variety of methods. Leveling or other ground surveys are used to measure relative height differences across profiles, using optical and electronic instruments to measure distance from an observation point. Slope and aspect are two commonly used terrain variables. They are required in many studies of hydrology, conservation, site planning, and infrastructure development, and are the basis for many other terrain analysis functions. Slope is defined as the change in elevation with a change in horizontal position. Aspect is also an important terrain variable. Aspect is used to define the direction water will flow, to estimate the amount of sunlight a site might receive, and to determine what portion of the landscape is visible from any viewing point. The aspect at a point is the steepest downhill direction. The slope command takes an input surface raster and calculates an output raster containing the slope at each cell. The lower the slope value, the flatter the terrain. The higher the slope value, the steeper the terrain. The output slope raster can be calculated as percent slope or degree of slope. So there's two ways to report slope, degrees or percent, like I just said. The percent rise can be better understood if you consider it as the rise divided by the run multiplied by 100. When the angle is 45 degrees, the rise is equal to the run, and the percent rise is 100%. Okay, so I'm going to do a really quick demo on how to create a slope, and you'll be going over this in Lab 10. So I have my digital elevation model layer here that I've named Arcata North-South. And so the first thing that I'm going to do is I am in my Arc toolbox. I'm going to open up my Spatial Analyst toolbox. And then I'm going to go down and open up Surface. And then I'm going to double click on the slope function. And I'm going to include my input raster. In this case, it's going to be Arcata North-South. It's the only layer that I have in my map. And this is just a good reminder for everybody, especially with working with raster files, because they're so large, it really takes a long time for ArcMap to process. So please be patient and don't overclick, because you will cause the program to crash. And if you haven't been saving, that could really set you back. So again, patience is really important here. Okay, so I have my input raster, and then my output raster I'm always going to put into my working folder, because any of the data that has been manipulated or changed is no longer original data, and so we want to make sure that we're keeping everything organized. Okay, so since I already went through everything, I created an extra working folder just so I don't get my other data layers confused. So I'm going to tell it to please save in my working lab demo. Oops, double click that. And then I'm going to name my new layer slope. Okay, so like we were talking about before, there's two ways to represent our measurements. We've got degree and percent. For this exercise, we're just going to leave it at degree, and we're going to keep everything else the same. And I'm going to click OK. So I'm not sure if you could see it here in this screen. I've extended it as far as I can down, but there's going to be like a little globe down here that is going to be spinning, and it's letting you know that the program is working. And again, be patient. Try not to do anything else in ArcMap until you get a little blue box that will show up down here at the bottom to let you know that that slope has processed.